So I think we can start. I hope I am audible and my screen is visible. So good afternoon, Akshay. Okay. Um, so let us start with the discussion session 6 of natural convection heat transfer and diffusion mass transfer. And so far we have covered introduction, mathematical analysis, problem session 1 and some special cases. And we will be combining together combined free and forced convection and discussing some problem discussion with regard to that. So by that, we will be coming to an end to free convection by today. Okay. So we are coming to an end of free convection or a natural convection by today. So, so today we will be having discussion of 3 important problems which are actually related to mixed convection. So let us quickly go to question number 1. So question number 1. So see the question. So square panels which are 250 mm by 250 mm, which is the dimension of this. So with a decorative, highly reflective plastic finish are cured in an oven. So it's an oven. It is at a 125 degrees Celsius. And after curing that plate in oven, it is now taken outside and left to cool in ambient air at 29 degrees Celsius. So the quality considerations says or dictate that the panel should remain horizontal and that cooling rate can be controlled. Cooling rate can be controlled. So to increase in the productivity in the plant, it is proposed to replace the batch cooling method with a conveyor system having a velocity of 0.5 meter per second. So initially, there was actually only stagnant cooling. So if something is cured at 125 degrees Celsius, it is left to cool 29 degrees Celsius in ambient. Now what happens is replacing that system with another cooling method or a conveyor method, and it is given an initial velocity of 0.5 meter per second. So this moves at 0.5 meter per second and air is quiescent or air is stationary and at 29 degrees Celsius. So we are asked to compare the initial, which is actually immediately after leaving the oven. So oven may be here. In convection heat transfer for the two methods. So we have to find what is the heat raised happening through both methods. So in initial or batch method, there is only natural convection, QNC. So when it comes to conveyor method, there is mixed, which involves natural convection as well as forced convection. So it is actually QNC plus Q forced. So we need to compare how much. Obviously, we know that Q mix should be larger, but how much? That is the question. Okay. So in this question, actually, we are going to assume quasi-steady state. Okay. Quasi-steady state. Then backside of the plate are insulated. So we assume that heat transfer is happening only from the top surface. So all other sides and all are insulated. Okay. Then airflow is in the lengthwise. So airflow is happening in the lengthwise direction. So if the plate is like this, airflow will be happening this, not in this direction or something. Okay. Then the fourth assumption, constant air properties. Constant air properties. Fifth assumption, Q radiation is very less than Q convection. Also conduction also we can assume it's very negligible compared to convection heat transfer. So for air, we need to calculate the properties at mean fluid temperature, which is Tf plus T infinity by 2. So that will be 350 Kelvin. Okay. So that is actually our 350 Kelvin. So we will evaluate it at 1 atmosphere from the heat and mass transfer data book. We will evaluate the properties of air. So that is nu is equal to 20.92 into 10 raised to minus 6 meter square per second. Okay. Then thermal conductivity K is equal to 0.03 watt per meter Kelvin. Alpha is equal to 29.9 into 10 raised to minus 6 meter square per second. Prandtl number equal to 0.7 and data equal to 1 by Tf, which is the TMF mean fluid temperature. That comes to be 0.03. Okay. So initially we will assume free convection. Okay. So we know Q is equal to H bar into A into Ts minus T infinity. So we need the Nusselt number. So before that, we will evaluate the Grashof number. Grashof number is G beta delta T LQ by nu square. So that comes to be 9.8 into 1 by 350 into 125 minus 29 into 0.25 cube by nu square. Nu is 20.92 into 10 raised to minus 6 the whole square. So that value comes to be 9.597 into 10 raised to 7. Similarly, we can calculate the Reynolds number if it is moving at a particular speed. Okay, Vd by nu. So V is 0.5 into, it's not D, it's actually L because it's the length of the plate. So 0.25 by nu. So it is 20.92 into 10 raised to minus 6. So that comes to be 5.975 into 10 raised to 3. Okay. So is it in the laminar or turbulent region? So it's a plate case. So plate Reynolds critical number is actually 5 into 10 raised to 5. So this is less than that. So it is laminar region. Here also it is in the laminar zone. Okay. So we will calculate the Grashof to Reynolds number square, which I have mentioned for in the case of a mixed convection. This number, which is also called as a Richardson's number, is very significant. So we will calculate that value. That comes to be 2.69. Okay. So which means that Grashof is greater than Rayleigh's. So there is natural convection happen. Okay. So we also calculate the Rayleigh number. Rayleigh number comes to be GR into PR, which is equal to 6.7187 into 10 raised to 7, which is actually in the laminar zone. Less than 10 raised to 9. Okay. So we will use the appropriate correlation. Nusselt number average is equal to H bar into L by K average, H bar into L by K, which is equal to 0.15 into RAL raised to 1 by 3, which is for the top plate or the hot surface. So that comes to be 0.15 into 6.718 into 10 raised to 7, the whole raised to 1 by 3. So that value comes to be 60.9. Okay. Now from that we can calculate the H bar value. H bar comes to be 7.31 watt per meter square Kelvin. Also we can calculate the Q value. Q is 7.31 H delta T into length into width. So 0.25 into 0.25 into 125 minus 29. So that comes to be 43.9 watts. This is actually due to natural convection. Now, if it is moving with the Reynolds number REL, which is 5.975 into 10 raised to 3, flow is laminar. So we can use the correlation. This is there already for a flat plate. That is 0.664 into RE raised to half, PR raised to 1/3. Okay, so that comes to be 45.6. So this is in the moving case. So there is force convection. Okay, so we can denote it by NUF. And this we can denote it as NUN. Okay. So NUN is 60.9 and this is 45.6. Okay. So how can we calculate the combined value? How can we calculate the combined value? Yes, for combined value, NU raised to 7/2. This is for a flat plate, okay? NUF bar raised to 7/2 plus NUN raised to 7/2. This correlation is available for flat plates, okay? So that value comes to be 45.6 raised to 7/2 plus 60.9 raised to 7/2. So that value comes to be 66.5. Some kind of it's an average kind, okay, between them. So H bar correspondingly combines to Nu into K by L, which is equal to 7.99 watt per meter square Kelvin. Okay, so Q is equal to 7.99 into area, which is 250 into 10 raised to minus 3 square into 125 minus 29. So which is equal to 47.9 watts. So this is actually mixed. What was the natural convection initial case? So that is 43.9 watts. So what is the delta Q? 47.9 minus 43.9. That is nearly 4 watts. So there is a slight increase only in heat transfer. So this method doesn't add much to the heat value. So why is it? Because we have previously calculated Grashof by Reynolds square. In this particular problem, this dimension, actually Grashof is actually greater than Reynolds square. So natural convection is more effective. So either we need to move that conveyor at a higher speed or something so that it will cool very faster. So this method is not much favorable, but there's a slight advantage in the cooling rate. Okay, so that's about that problem. Okay. So next problem, second problem, is a very kind of interesting problem. Like it's not conventionally, it's not a conventional problem. It's a theoretical kind of question. We are trying to derive a relationship which is actually not mentioned in many of the books actually. So this problem is very interesting. So the question is of the type mixed convection. So it's a mixed convection near a vertical wall with suction. So there is a vertical wall like this. It can be our building walls, maybe. Or it can be any of our some apparatus or some kind of a chip through which water has entered. So what happens is there is a mixed convection. Assume that it's happening near a vertical porous wall. So the wall is actually porous. Okay, so through the porous wall, there is actually suction velocity, or the water is actually going outside with velocity Vc. The question is determine the temperature and velocity distribution, and also the friction coefficient Cf. So we need to identify the contribution of natural convection and discuss. So the question, if you analyze, the wall is at temperature TO and the ambient is at T infinity. So there is actually natural convection happening around the wall. So you can see the boundary layer growing over the wall. It is heated kind of condition. So the velocity layers are getting formed. So you can see here. So one thing you need to identify is that it is given in the problem that introduce some kind of a dimensionless variable eta is equal to V0 y by alpha. So introduce something like this so that the temperature distribution obtained for this. So this is just a hint. It's not a problem. So the important part of the question is it is happening like a suction from the wall, right? So the water is getting continuously absorbed or it is going outside. So what is the effect of that? So one important effect of that is this suction actually prevents the growth of this thermal boundary layer as well as velocity boundary layer. So you can see that growth is there, right? You can see. So if we say d delta by dx, so if x is this direction, y is this direction. So change in the delta or the velocity boundary layer thickness as well as delta T by dx, thermal boundary layer, is 0 because the suction is happening. So there is whatever air or heated air comes out to the porous walls, it is going outside. So the growth of the boundary layer is actually disrupted. So it will come to a flat-like condition. Okay. So let us solve this problem. That's a very kind of interesting thing. So let us see how that is getting solved here. So we will start with, we know our basic governing equation, right? So what are the basic governing equations? Continuity equation, conservation of momentum equation or Navier-Stokes equations, and energy equation. So continuity equation, this is an xy plane. So dou u by dou x plus dou v by dou y equal to 0 for 2D incompressible steady state equation. And regarding Navier-Stokes equation, you know what is the case? U dou u by dou x plus v dou u by dou y. This is in the x direction. X, y is equal to minus dou p by dou x or dp by dx plus mu into d square u by dy square, plus if there is some body force, that force is also there. So that we can denote it as rho g b or something. This is actually minus. Then energy equation. What is energy equation? Energy equation is u dt by dx plus, so this is actually a rho, okay, 1 by rho, because we have taken rho to the other side. Okay, so you have to divide throughout by rho. U dou t by dou x plus v dou t dt by dy is equal to 1 by alpha d square t by dy square. Alpha is equal to k by rho. It's thermal diffusive. Okay, so we know that actually d delta by dx is equal to 0 and d delta t by dx is equal to 0. Okay, so there is no growth of the boundary layer. So if you look at this equation, du by dx plus dv by dy equal to 0, right? So this is our x direction, y direction. So velocity in this direction is u and velocity in this direction is v. So the plate is like this. The flow is happening like this t infinity t. Okay. So du by dx is equal to dv by dy equal to 0. So we assume that this v equal to a constant. So if this is v, this is a suction velocity, right? It is getting suction. So that is actually denoted as VO, which is a suction velocity. So in the problem itself, it has been given that it's a constant. So it is not going to vary with respect to y. So dv by dy goes to 0. So just du by dx equal to 0 will be the continuity equation. So this continuity equation finally changes to this thing. Okay, du by dx equal to 0. So what does that mean? U is not varying with respect to x. So U is just a function of y. Similarly, we can see, similarly, what we can see, the growth of thermal boundary layer in x is 0. So similarly, we can see there is t is a function of y, or t of y minus t infinity. If you denote it as theta, that will be fine, the difference. T will be a function of y, t infinity is a constant. So just I am subtracting that also. Let that be in this format. So that will be useful in the further analysis. Okay. Now let us go to the analysis. So momentum equation, as I said, U du by dx plus V du by dy equal to, so we have seen this is going to be 0 because du by dx is not there due to the because it is not going to vary with respect to x. So V dou u by dou y. So what is V? It is a suction velocity. So since this is suction, we will denote it as minus VO. Why we are denoting it as minus VO? Because we have assumed x in this direction and y in this direction. So this is plus y plus x, and velocity will be in this direction, minus VO. So that LHS term comes to be minus VO into du by dy. Okay. And RHS contains, what are the terms in the momentum conservation equation? Is mu d square u by dy square plus dp by dx. So in natural conversion, that value is g beta into t minus t infinity. This has been already discussed. It's a buoyancy force. So the momentum equation actually changes to minus VO du by dy, okay, is equal to nu into d square u by dy square plus g beta into t minus t infinity. So actually, you can see here the unknown quantities are u and t. So we don't know the value of t. So for that, we need to go to energy equation, conservation of energy equation. Okay, going to that. So we have previously denoted theta, let theta equal to t minus t infinity. So we note that in mind. Okay, so somewhere if you are using theta, that will be t minus t infinity. So energy equation is like this: u dt by dx plus v dt by dy is equal to. So here also this term goes to 0. Just this term remains. So that is minus vo dt by dy. This will be the LHS. And the right hand side of that energy equation, as we know, it is alpha d square t by dy square. Okay. So we can just rewrite that. So energy equation becomes minus vo dt by dy equal to right hand side dou square t by dou y square. Okay, so this is simply a differential equation. We need to solve this. So rearranging that, you will get d square t by dy square plus vo by alpha dt by dy equal to 0. So solving that, d square t by dy square dt by dy, integrating it. the first integration and second integration, finally you will be getting an expression like t equal to C1 plus C2 e raised to minus VO y by alpha. So C1, C2 needs to be determined. So for that, we need the boundary condition. Okay. So boundary condition, what are the boundary conditions? So this action is happening at here at y equal to 0. What is the temperature? It is T equal to TO. And here at T equal to T infinity, at y equal to infinity. So as y tends to infinity, T equal to T infinity. So substitute that, you will get T equal to TO minus T infinity into e raised to minus VO y by alpha. So T equal to theta e raised to minus VO by alpha, theta O. Okay. So in the hints also, they have told us to assume like this. So that is actually we are approaching in the right manner. So we can just be clear that TO equal to, theta way, just we can. So I have made one mistake. It is theta equal to theta O into e raised to minus VO y by alpha. Okay, theta is actually T minus T infinity. Theta O is theta TO minus T infinity. Okay, so we got the temperature distribution. So we have the previously the velocity field, conservation of energy equation. So let us just substitute in that. You substitute in that, we know, substitute in that minus VO du by dy equal to V d square u by dy square plus g beta into T minus T infinity was our equation. So now we have T minus T infinity, this theta, right? So that is actually, so please note, why did we use theta notation? Because here it is T minus T infinity. So always in natural convection, the driving force is the temperature difference. So let us substitute that value. So that comes to be minus VO du by dy equal to mu into d square u by dy square plus g beta into theta O into e raised to minus VO y by alpha. So now it is a differential equation just in y. So if you rearrange d square u by dy square plus VO by mu into du by dy plus g beta theta O by VO. Sorry, it's mu. So that is mu into e raised to minus mu by alpha. So that will be the differential equation for the velocity. So if you solve that, you will get this is equal to 0. Okay. Differential equation for velocity of a ball with suction. We solve for u differential equation. You will be getting u equal to, suppose as indicated in that. So we are going to denote this VOY by alpha, which is equal to eta. Okay. So these kind of transformations are called as similarity transformation, which we had discussed in some of the previous classes. So we have just mentioned about this in the previous classes. So this similarity transformation, suppose if the particular velocity profile is a function of xy, maybe something like y by x into 1 minus y by x the whole square, etc., xy, etc. So we can just maybe substitute eta equal to x by y. So the two variables are removed and a third variable containing the two will be added. So such transformations are called as similarity transformation, and eta is called as a similarity variable. Okay. So currently we are going to substitute this with eta. So solving that, u will be a function of just eta alone. So we can obtain after solving e raised to minus eta plus C2 e raised to minus eta by PR plus u infinity. So in the initial question also they have mentioned this part. So please analyze this part. This has got this variable part, and this is the particular integral type, right? If we integrate a differential equation, this is a constant. Okay. So if eta is tending to infinity, u of eta is just u infinity, which means the outside condition. So as soon as it gets into this, here it is u infinity. So as soon as it gets inside, then this factor comes in. Okay. So please understand that point. So we can just determine C1 and C2 from the boundary condition. What are the boundary condition? What are the boundary condition? What is the boundary condition in this case? Yeah, u of 0 equal to 0 and u of infinity equal to u infinity, right? Is it correct? Okay. So u of eta by u infinity, we can rearrange just dividing throughout the previous equation by infinity. It becomes g alpha g beta theta o to nu square into 1 minus PR into u infinity into e raised to minus eta by PR plus 1 minus eta by PR. Okay, so why we rearranged like this? Let us tell. So you can see PR coming, right? So if PR is tending to 1, nu equal to alpha case, right? Because PR equal to nu by alpha. Prandtl number is equal to ratio of kinematic viscosity to thermal viscosity. So in that case, we can't use because 1 minus PR is here. So if PR becomes 1, then this goes to infinity. Okay. So the thing is, then that case is a limiting case. So we can apply the L-Hospital rule and see so that we will get the corresponding like a differentiation. So that in that case, it just reduces to nu into G beta theta O by nu square u infinity into eta raised to minus eta plus 1 minus e raised to minus e. So this looks like in a very rugged form, which is not actually satisfying. So let us try and rearrange it. Okay. So this is a mixed convection problem. So it's a combination of natural and forced. Okay. So Grashof number, which is equal to G beta theta O by mu square into L cube. We all know this, right? So, but there is no length scale in this problem so far. So what is a length scale? This L value. There is no height. There is nothing mentioned. So please note that in this case, the GR is denoted by LT, thermal length scale. So what is thermal length scale? This is simply alpha by VO. Because unit of alpha, if you look meter square per second, VO is meter per second. So the net unit is meters. So it's a thermal length scale because it is determined by the diffusivity of the fluid, thermal diffusivity of the fluid. If the One second. Okay. I hope my screen is visible. If not, please tell me. Okay. So Grashof number is equal to G beta theta O LQ by mu square. So in this problem, LT is a scale. So that comes to be mu by alpha. Okay. So we'll just rearrange the previous expression, that alpha G beta O. So that can be rearranged alpha G beta theta O by mu 0 square into 1 minus PR into U infinity. So that can be rearranged to get G beta theta O by nu square into alpha by VO cube into V by U infinity into alpha by VO. Just we are rearranging and substituting some value. So let us see. So what is the advantage of like this? If you rearrange, this is similar to Grashof, but that L scale is this value. So that can be written as GRLT, where LT equal to alpha by VO, which has got units in meters. And what is this thing? See, it is V by U infinity into L. So what is that actually? Reynolds number. But the length scale is L, L, R, E, L, T. So it is actually R, E, L, T. But this is inverse. Okay, because 1 by R is this value, because R is VL by mu. So this is reversed into PR by 1 minus PR. So that simply reduces to GRLT by RELT into PR by 1 minus PR. So that becomes our, see that expression, U theta by U infinity comes to be. So if Prandtl number tends to 1, then we have to use, what we have to use? This expression, U of eta by U infinity becomes GRLT by RELT. Okay. So this is for Prandtl number not equal to 1. Okay. So we have almost approached that problem. So we got a velocity distribution in terms of Grashof and this value. So finally, we have to substitute. This is a proportionality only. For final expression of U theta by UT, we just need to go back. So finally, we can see U eta by U infinity becomes GRLT by RELT into PR by 1 minus PR, which was our that coefficient we rearranged, into eta raised to minus eta raised to minus eta by PR plus 1 minus eta raised to minus eta by PR. Similarly, if PR, this is for PR not equal to 1. If PR equal to 1, then this simply reduces to GR RELT into e raised to minus eta raised to minus PR plus 1 minus e raised to minus eta for PR equal to 1. So you can note here one important observation. We have said about Richardson number, which is Grashof by Reynolds square. But here you see it is Grashof by Reynolds only. So why is this? Because this is actually because the inertia term. because Reynolds number is equal to inertia force by viscous force. So in inertia force, U is proportional to V only from the conservation equation, because suction velocity is constant. That's why it's not RE square, it's REL. Also, we can see the first term is actually existing. If in the case, if suppose RELT is very much greater than Grashof number, then this goes to 0. Only this term exists. Okay, so you have to understand that part also. So this is due to natural convection. This is due to forced convection. Similarly, one question asked is CF. CF is equal to tau W by rho V square. Okay, so if that is the case, just mu dou U by dou Y at 0 by rho VO square. So that comes to be U know G beta theta O by mu O cube into PR plus U infinity by mu. So just note that expression, just substitute that and see. So this problem is a suction problem. So suction is happening at velocity VO through the porous walls. Okay. And then we have obtained the temperature distribution first. From that, we will get the velocity distribution in terms of Grashof by Reynolds. From that, we are calculating the CF cases. Okay. So we'll be having one last problem. And if we get time, it's actually a bit lengthy, not lengthy, but let's analyze this very simply. Okay. So just have a look at this problem. So heat generation inside a fluid plays an important role in nuclear power plants. So this is actually analyzing our basic governing equation. So it's very important that you understand. So in a heat generation in nuclear power plants, in chemical reactors, so natural convection is actually present. There will be transport of the heat from the fluid. So there is a parallel piped. There's a parallel piped here you can see of width D and height L. So parallel piped is something like a, it's always parallel. Okay. So width, height and LD and span length. Span length LZ is very much greater than D, comma L. Span length is a length through which that it's spreading. So the heat transferred or something. So how much, if L is the height, still it can traverse inside. So that is a span length, LZ. And heat is generated at a uniform volumetric rate. So this is Q triple prime. This is actually per meter cube of the fluid. And the fluid is constantly cooled by the vertical walls. In nuclear reactors and all, suppose in nuclear reactors and all, the fluid will be cooled by the vertical walls at constant temperature TO. Horizontal walls are adiabatic. Find 4 relations between the different scales and parameters of the problem by considering energy equations in the central region. So there will be a center region or the core region. And energy equation in the boundary layer. You can see a delta. Boundary layers are formed. So the fluid here is not air. It can be any chemical fluid which is actually taking part in this nuclear reaction. Then Bose-Einstein equation X in the boundary layer. So how does that vary when there is Bose-Einstein approximation happen? Then conservation equation of flow rate. So the question is, solve the system, deduce from the result an order of magnitude analysis for the Nusselt number that characterizes the heat transfer between the fluid and walls and for the total heat transfer per unit QLZ, unit length QLZ. This is Q per LZ. Okay. So if LZ is the span length, maybe it will be some LZ. Okay. Q triple prime ISSS. Okay. So there is a core region, which is a central region, and there is further after that, there is a boundary layer, which is the towards the walls. And we'll be solving this just from the basic. So we assume there is a simplified flow in this problem. And the flow and heat transfer are 2D, steady, symmetric with respect to the vertical axis of the cavity. And fluid motion is governed by the perfect fluid equations in the central part. It is characterized by uniform velocity u. So in the central part, there is actually perfect fluid equations are followed. And we denote the central velocity by u1. There is a core region. U, and in the boundary, we will characterize by u1. So in the boundary layer, we will denote it by u1 and delta to be the boundary layer thickness. So if anywhere delta T is used, that is T1 minus T0. It's the temperature scale. Okay. So let us start with analyzing the equation. So first we will take the central region. So we will go to the energy equation straightly. So in energy equation, we know u dt by dx. So this is x, this is y. Okay. So u dt by dx comes to be, there is a uniform volumetric heat generation, Q triple prime. So it comes to be Q triple prime by rho Cp. So what happened to the other terms inside this? They all go to negligible. So I have told us order of magnitude analysis. So even in the first discussions and all, I have said, suppose in a term which contains 1 by delta square, if delta is very, very small, suppose 0.001, then 1 by delta square will be very large. So that terms will be taken and other terms containing 1 by delta and all will be neglected, or delta will be neglected. So that is the order of magnitude analysis. So from that you will be able to easily obtain some simple expressions which are actually not exact, but they are dimensionally similar. Okay. So if you take u, so in the central region, if you assume u, dt becomes delta t. Okay. And x becomes the length. So in the core region, we can assume that is dimensionally similar to, order of magnitude is similar to q rho by rho c. Okay. So that's called as an order of magnitude analysis. So all other viscous terms and other d squared T diffusion terms vanishes, because in the central region we assume uniform velocity as mentioned in the question. So only this term persists. You can just see. And the temperature gradient in the dt by dy is also not considered in the core region if needed. So that is in the central region. Now let us go to the boundary layer region. So there actually these gradients are existing. See, in boundary layer actually what is happening? It's not simply u dt by dx. So in the boundary layer only that factors are happening, that gradients are existing. So that's why it's called as a boundary layer, right? Thermal boundary layer or velocity boundary layer, because gradients are existing in the boundary layer. But outside that, there are no gradients like that. Okay. So if we go to that, just we can modify the same equation u dt by dx plus v dou t by dou y equal to alpha d square t by dy square, which is actually significant. Doesn't mean that dou square t by dou x square exists, but it's very less. Similarly, there are heat generation, volume heat generation, Q by rho Cp. So this is actually similar to, you have to think like this. Whatever energy comes in must be equal to energy out. If there is E generated, that is this factor. Here also it's the same. So here actually what is happening? There's a central region. There is heat generated inside. So heat will be convected and it will be going out. So that is actually modified in this equation. Okay, so you have seen this equation, right? So this is for the boundary layer. So central region, we have seen that the value U delta T is similar to Q triple prime by rho Cp. So in the central region, this is the magnitude. So if you rearrange, U is similar to QL by rho Cp delta T. So we can get the order of velocity in using these values. So here you just analyze, this becomes U into delta T by L. Okay, and V delta T by delta Y. dy will be very lesser. So V into delta T by dy. What is dy? Yes. What is dy? So if delta T y is taken, we assume that temperature gradient is very minimal in this. So this term can be neglected. So what is persisting is alpha delta T by delta T square, delta square. So dou square T scales with dy. So in the thermal boundary layer. So if we look at this, here also it is V delta T by delta. Okay. So that is there. Then Q triple prime by rho Cp exists. So we have to notate this by U1 because it's in the boundary layer. Okay. So I'll rewrite it again. So U dt by dx plus V dt by dy. This is for boundary layer. Okay. Boundary layer or the towards the wall. Is equal to alpha d square T by dy square plus Q triple prime by rho Cp. Okay, so we will rewrite this U1 into delta T by, just notate this, not adding anything. V into delta T by delta, and this becomes alpha into delta T by delta square, and this becomes Q triple prime by rho Cp. So we are going to neglect this term, okay, and also this term. Why? Because we think that although the uniform heat generation rate exists between that, so that heat generation rate is actually negligible inside the boundary layer. So it will be more prominent in the core region, but in the boundary layer, that effect is negligible. And also this term, V delta T by delta. So that is actually not much effective because V is actually tending to 0. Okay. So this is U, this is V, X, and Y. So simply this is scaling with alpha delta T by delta square. So this is the notation, scales with LHS, scales with RHS. So from that you will get U1 equal to alpha into delta T can be eliminated, alpha into L by delta square for the boundary layer region. So core region, what was the expression? Their core region, that Q triple prime comes in. Q triple prime into L by rho Cp delta T. So here you see delta T is not a factor. So here the alpha, L and delta square, that are the factors. Okay. Now the next question asked is, what if the Bose-Einstein approximation is used? Okay. So the Bose-Einstein approximation is used means the same equation U dou U by dou X plus V dou U by dy is equal to minus 1 by rho dp by dx plus g beta t minus to plus mu d square u by dy square. So this term, actually when Boston's approximation is used, we know these terms actually goes to 0 in the other scale. So P can be assumed to be a function of P plus rho gx. This has been previously discussed. So in a boundary layer, inside a boundary layer, in the vertical direction, so just we can replace this. So this terms goes to 0. Okay. So this simply reduces to minus 1 by dp by dx plus g beta into t of x minus to equal to 0. So this is T core of X. So this is the core temperature. So that is actually assumed to be almost stable. It varies with respect to X rule. Okay. So we can replace that in these equations to get U dou U by dou X plus P du by dy is equal to G beta into Tc minus Tc of X plus mu d square U by dy square. Okay. So here also we will do the order of magnitude analysis, then U1 square, because this is in the boundary layer, U1 square by L, because this is U1, this is of the order U1. So U1 into U1, U1 square, and this is actually negligible. And this becomes G beta delta T. And this becomes mu into U1 by delta square. Okay, so this can be combined. So this scales with this value. This also scales with this. So we can use this because we need G beta. So U1 square by L G beta delta T and V U1 by delta. So from that U1 we will get U1 square is equal to G beta delta T. So it's not equal, it's scaling. G beta delta T by Prandtl number. Mu by alpha comes. Okay. Now conservation of flow rate. That was the second question. So if we consider a horizontal section XX, there will be fluid passing. So there will be a core region and there will be a boundary region. Right? So the total flux should be 0. So 0 to delta U dy plus delta to d by 2 U dy, capital U dy must be equal to 0 for continuity equation. So if we integrate U1 into delta plus U into d by 2 minus delta equal to 0. Or in scaling, we can just write, bring it to other side, ud. U1 delta scales with ud. So please note boundary layer velocity and the core velocity are appearing by this relation. Okay, now calculation of characteristic scales. That is the next part. So just we need to characterize the constants. Okay, we're using all these expressions. Okay. So we have all these expressions. First expression was U1 equal to alpha L by scales with alpha L by delta square. right? And previously before that, U was with Q triple prime into L by rho Cp delta T core. This is boundary layer. Then we have the U1 square G beta delta T L by PR using Bose-Einstein. Then comes U1 delta is scaling with UD, conservation of flow rate. So combining all this, you have to eliminate delta. You have to get an expression for delta in terms of that relation. So if you combine all this, we will get just eliminating the values you can obtain. Just eliminate U1 and U. Okay, U1 and U just you need to eliminate. So delta raised to 5 scales with mu alpha k by G beta Q triple prime into L by D. Eliminate U1 and U from all this. Okay. But we are going to define Rayleigh number based on this Q triple prime or RAL. So that will be G beta Q triple prime by mu alpha k into L raised to 5. So this is a new Rayleigh number, suppose defined. You can see similar Rayleigh number in a constant flux condition. This has been discussed in the first sessions, second sessions, and all, based on constant heat flux. So just replace that here. You can see delta raised to 5 is approximately, scaling with how much? L raised to 5 into L by D into 1 by RA. Or bring it to the other side, it becomes delta by L raised to 5 scaling with 1 by RA into L by D, right? This expression. So delta by L is scaling with RA raised to minus 1 by 5, L by D raised to 1 by 5. Okay. Now we can use this delta by L value here in this expression. Okay. So then first expression we got now, delta by L scales with RIL raised to minus 1 by 5 into L by D raised to 1 by 5. Well, U1 into L by alpha raised to RA L raised to 2 by 5 into L by D raised to minus 2 by 5. UL by alpha, similarly, we can see, just rearrange that RIL raised to 1 by 5 into L by D raised to 4 by 5. Also, the value of delta T, that comes to be nu alpha by G beta L cube into RAL raised to 4 by 5 into L by D raised to minus 4 by 5. And Nusselt number, which is our interest, this is Q triple prime. Is it Q triple prime? No, it is heat flux K delta T by X. Okay. So from the continuity equation itself, we can see temperature equation we know. This actually scales with L by delta. Okay, because Q double prime is equal to, it's a flux Q delta T by delta. So this you can check using scaling in energy equation. So this finally, because Q prime is going to be, flux is actually Q delta T by delta. Because Q double prime is equal to K delta T by delta. Okay, so Nusselt number comes to be just simply RAL raised to 1 by 5 L by D raised to minus 1 by 5. Because L by delta we have already determined here, delta by L. So that is has to be used. This is the reverse. So this is for the constant volumetric heat generation. So it is actually, you see, it is independent of the, it's already dependent on the length to diameter ratio and the Rayleigh number. So if you change the geometry size and all, just you can see how that is going to affect the Nusselt number. If the L by D ratio is going to be 5, it is going to be 2, it is going to be 0.5, then you can see how that is going to affect this Nusselt number. Okay. So the heat transfer to the wall, you can see, is actually Q triple prime, Q double prime into Q double prime is equal to Q triple prime into D. So the total heat transfer rate also can be determined. So that is Q double prime into D into L. So that value is also you can determine through this approach. So this was just an understanding. You can just go through this once again after this video has been uploaded, so that you will get a better understanding. So currently this is with reference to convective heat transfer in John by Favre and Marinette in published by John Wiley book. You can refer to that. There are some problems in that. So that is actually one important analysis of this kind of mixed convection and problems. So in where different kinds of situations are come. So you can just refer to that and understand. So today we have discussed this part, natural convection, heat generating fluid, then with suction and mixed convection numerical problem, so that you can understand. In the next session, we will be moving on to diffusion mass transfer, which is mass transfer or the addition or removal of mass. Okay, so far we have taken heat. The driving force was temperature difference. The other driving force will be concentration difference. So how that is driving the heat transfer. Okay, so we will be discussing about Fick's law, how that is affecting this diffusion. So we'll be all discussing in detail about that problems. Okay, so that's all for today's session. If you have any doubt, you can ask. So okay, I hope it's almost clear then. Thank you. See you next Sunday regarding the class. Okay, fine. Sure. See you in the next class.